Welcome to Oddly Real. I'm Nem Stefanovic. Black holes are one of the most powerful and extreme objects in the universe. They take the laws of physics to the limit. Nature also seems to conspire to hide their inner workings from us and the rest of the universe by shielding their cores with an outer layer called the event horizon. Despite the mystery of their inner workings, there are some astonishing characteristics of these objects that exist on the outside of the event horizon. For example, black holes are completely dark at their core, yet they can induce surrounding gases to generate so much heat that they can shine brighter than entire galaxies. Black holes are among the most efficient and abundant sources of energy, far more energetic than stars. They could provide highly advanced civilizations with tremendous amounts of usable energy. Finally, a black hole consumes any object that enters its event horizon, with no chance to return to our universe. Yet, surprisingly, black holes can and do shrink in size, eventually ceasing to exist, a kind of black hole death. In this episode, we'll explore these amazing properties of black holes. The gases and matter surrounding black holes are pulled toward the event horizon by gravity. The closer the gases are to the hole, the stronger the pull. As they get pulled in, they collide with nearby particles, which cause the gases to heat up to temperatures upwards of millions of degrees Celsius. The atoms of the gas molecules vibrate fast enough to produce high-energy electromagnetic radiation like X-rays and gamma rays, which are detectable at great distances. Gases also take spiraling paths towards the hole as they're pulled in. They circle many times before they fall into the hole. This creates a disk-like shape, an accretion disk, for the gases around the hole. It is a source of brilliant light emissions, sometimes being able to shine hundreds of times more brightly than the most luminous galaxies. There is a ring of light around supermassive black holes. This is due to gravitational lensing, which is the force of gravity bending the light around the hole. The light consists of light from behind the hole and other directions, as well as duplicate images from the same stars where light takes orbiting paths around the hole before it comes into view. If you were to descend close to the surface of the event horizon and look up, you'd only see a small viewing area back into the universe with total darkness surrounding you below and to your sides. The powerful gravitational forces would be bending light down to your view from above, but the actual light sources would be coming from many directions. They would come from directly above, from the sides of the hole, and even behind the hole. There would also be duplicate, triplicate, and higher copies of images from around the hole due to orbiting light paths. If you are close to a black hole, any signal transmissions that you send outward will experience a redshift. For example, you can transmit information using visible light with a certain color. However, that color will not be the same as seen by the receiver of the message who is further away from the hole. It will be shifted more towards red, or even weaker parts of the electromagnetic spectrum, like infrared, microwave, or radio waves. The closer you are to the black hole, the more significant the redshift. This redshift is due to gravitation, since the flow of time slows down closer to the hole, and the light frequency is determined by the passage of time where the light is emitted. So what happens when the force of gravity starts to pull you in towards a black hole? Let's assume a probe is sent towards the black hole, transmitting messages on its way down. The transmissions, using a laser light of one color, start to get redshifted as the probe falls faster toward the event horizon. This redshift isn't due to time dilation, but instead due to the motion of the probe as it accelerates toward the hole. When the probe is very close to the hole, the signals start to rapidly change from visible light to infrared to microwave to radio wave, and then finally they're undetectable. The probe is through the horizon. The last few signals sent back were actually sent well before the probe crossed into the black hole, but they took such a long time to travel away from the hole, they were essentially just remnants of the past, an echo of the probe signal. A black hole can also rotate. As it rotates, it drags spacetime around with it. This rotating spacetime happens outside of the event horizon. So technically, a sufficiently advanced civilization could extract this energy and use it for useful purposes. The amount of stored energy is enormous. For example, our sun converts a small part of its mass, 0.6%, into energy in the form of heat and light over its entire lifetime. In contrast, a rapidly spinning black hole would be able to convert up to 29% of its total mass into usable energy from its rotational energy. If this was all used up, the hole would no longer be spinning. There is evidence that many galaxies possess gigantic black holes at their centers, including our own Milky Way galaxy. There are estimates that put the black hole at the center of our Milky Way galaxy at 4.3 million solar masses, or 4.3 million times more massive than the Sun. Yet, there are far more massive black holes, such as TON 618, which is over 18 billion light years away, with a mass of 66 billion solar masses, according to NASA. If one of these supermassive black holes is particularly bright due to an accretion disk, it is typically called a quasar. Quasars can develop an accretion disk with so much energy that it can shine hundreds of trillions of times brighter than our sun. Additionally, they also produce very powerful jet streams of hot gas that are launched out above and below its axis of rotation. These jet streams can be so powerful as to launch out hundreds of thousands of light years into space. There are multiple mechanisms that contribute to the production of these jets. The accretion disk spinning near the hole expands out and thickens due to the enormous pressure from the high heat, which guides the gases through narrow tunnels along the axis of rotation. There are also magnetic field lines from the accretion disk that are trapped within the center of the disk, and their rotation guides plasma up and down along the jet streams. There can also be a cooler cloud of gas surrounding the hotter accretion disk. The cooler gas cloud blows up like a bubble due to the hotter gases from the spinning accretion disk. This bubble inflates, but holes in the top and bottom form to expel the hotter gases out. A truly astonishing discovery about black holes was made that they do not exist forever. This is a surprise, since nothing can escape their grip once inside the event horizon. If anything, they grow in size when they consume more matter. However, they shrink over time due to the effects of Hawking radiation, and then ultimately explode. The radiation itself takes many different forms, including electromagnetic, gravitational, and neutrino radiation. The energy that powers this radiation has to come from only one place, inside the black hole. But how does that happen? We know tremendous gravitational forces keep all forms of matter and energy locked up within the horizon of the black hole. The mechanism is due to the presence of virtual particles in space. These particles appear and disappear in the vacuum of space with typically very short existence. Two such particles, like photons, neutrinos, or even more massive particles, can appear, but they would quickly annihilate each other. However, around black holes, two virtual particles can be quickly pulled apart from each other due to the powerful tidal forces. Tidal forces are gravitational forces that will simultaneously stretch and compress objects near gravitational objects, including black holes. The tidal forces will supply the particles with the required energy to keep them from recombining, and hence solidify them as real, permanent particles. One of the particles radiates away from the black hole, while the other falls back in. However, the energy that was supplied by the hole to make this happen is lost to the hole, and the mass of the black hole actually shrinks a little. This process works for any type of radiation. It depends on the type of virtual particles that were created. The black hole's horizon has a finite surface temperature that is proportional to the hole's surface gravity. That sounds strange. How can a black hole have a surface temperature, especially since the surface of a black hole is only made of curved spacetime? The surface temperature is actually an apparent surface temperature. It acts as the temperature that an object would have based on its radiation emission. The black hole also has entropy proportional to its surface area. Entropy is a measure of possibilities. It turns out that the entropy of a black hole is a measure of the number of different ways that the black hole could have been created to obtain its observed state. Perhaps one of the really fascinating aspects of all of this is that the laws that govern black holes are the same laws that govern thermodynamics. In thermodynamics, the second law states that the entropy of the universe tends to increase with time, since matter will tend to move towards higher states of disorder. If we take matter and throw it into a black hole, the universe will actually lose entropy, since there will be less matter. However, we can now see that the entropy of the hole itself goes up. So in fact, the total entropy of the black hole and the universe combined goes up, which adheres to the second law of thermodynamics. Conversely, when a hole radiates away energy, the entropy of the hole goes down, but radiation is now returned to the universe. And once again, the overall entropy as the combination of the universe and the black hole goes up. Again, the laws of thermodynamics are preserved. Let's take a black hole that has a certain mass and is spinning. As the hole radiates away its energy, the spin would start to slow down until eventually the spin halts. Interestingly, even when the spin has gone to zero, the hole continues to radiate, powered by tidal forces and the mass of the black hole itself. As the black hole emits radiation, it's converting its own mass to energy, so the black hole shrinks. When the black hole shrinks, it becomes hotter, since its temperature is inversely proportional to its mass. When the black hole shrinks to the size of an atomic nucleus, it'll be incredibly hot, at over 1 trillion degrees or more. The result is a violent explosion over a tiny fraction of a second. If we look at a black hole that's relatively small at 2 solar masses, this type of radiative evaporation would require 10 to the power of 67 years, which is 10 to the power of 57 years longer than the age of the universe. I hope you enjoyed this episode. Remember, oddly real, really interesting.